Exphormer is another transformer in search for subquadratic complexity, and this time it does quite a good job from the looks of it, and it does so in a mathematically sound way, and they show some proofs unlike most machine learning papers, which is very, very nice to see. So this shows that their method actually is mathematically sound, so it's gonna work in theory and hopefully in practice. You never know with machine learning, but it actually does work in practice, and it does work pretty well. So Xformer basically takes the transformer, converts it to a graph. A transformer is basically a graph, the attention mechanism, or it is rather, and then they manipulate it in that space as opposed to manipulating it in a sequence and token space. So to start, we have attention, and attention is just this sequence to sequence relationship. So you have some tokens here, and the tokens represent words. So this would be like the cat, sat, and so on, like usual. And you throw this through your transformer. Specifically, we'll be looking at attention, not the transformer. And this gives you out your tokens after the attention mechanism. And this will be the cat, sat, and well, rather this would be, say, token 1, token 2, and token 3, where this one is a combination of these three, and each of them are a weighted combination. So the way you do normal attention is you take a sequence. I'll draw it down here. So you take a sequence, which is of shape n by d, and you construct three matrices. So you do three linear projections. This will be your queries. These will be your keys, and these will be your values. And you just do three linear projections. So this will be n by d, n by d, and n by d. And this first one will be via, this is our x, so our input. This will be wq. This will be w, I do not like where that's drawn, wk. And this will be wv, where the w matrix is in rd by d. So just linear transformations. And then you construct this matrix by doing queries, keys, transpose. So qkt, which basically tells you your routing mechanism. So if this was 3 by 3, say the cat sat and the cat sat, and if we make this causal by masking out the diagonal, we basically get this causal attention scheme. So after applying the softmax, so the formula is given by attention is equal to softmax of qkt times the values. We'll do that times the values. So this part here basically is your routing mechanism. So you get your probability scores here, and you basically have this causal routing mechanism, which is a graph, and then or which is basically a fully connected graph without this mask up here. So maybe cat is going to be composed of 0.1 of the, so there's not that much information for the, and then 0.9 cat, and then the word sat, maybe it needs to know what is doing the action, so 0.3 cat, 0.6 sat, and 0.1 the. And then you multiply these by the values, and you get out your output matrix here. So this will be, say, y. So your attention times your values. And basically your first token is going to be composed of only the second one is going to be composed of 1% of the and 90% of the cat. And then the last one will be 1% of the, 30% of sat, and 60% of, or 30% of cat and 60% of sat right here. So this defines a graph. And this is just our normal attention mechanism, but yeah, this defines a graph, and this graph in this case will just be 3 points. So it'll look like this, just a fully connected graph. the cat sat. So, I mean, this example isn't that interesting because we only have 3 points, but say we expanded this to more points. Maybe the cat sat on the mat. Good old sentence. So in this case, we have n is equal to 6, so 6 nodes, and you basically have a graph with 6 nodes in it. So 1, 2, 3, 4, 5, 6. Now the attention mechanism here or the routing matrix here would be a 6 by 6 dimensional matrix, and this would represent a fully connected graph here. I'm not going to draw out every one of these edges, but you can imagine if this was the word the cat sat on the mat. The distances are arbitrary, of course. Then you would get a graph where the sends information to all the words here, assuming it's not causal, so removing this part. Where the sends information to all the words, and then cat sends information to all the words, so cat would send information to the, and if it's causal, it wouldn't, but it would send information to the, it would send information to sat, it would send information to on, and it would send information to the other the, and then to mat. And this part right here was just our 3-part sequence. And then the next word, sat, would send information to the rest of the words, and so on. So attention, all it is a fully connected graph. Now, a graph neural network basically this is basically just a graph neural network with a fully connected graph. That's all attention really is with the softmax nonlinearity and no function transformation. So they basically look at it through this context where this is a graph. It's not necessarily it's not a sequence that you're looking at. It's just a graph, and looking at it through this context basically allows them to approximate this graph in a way so that they get linear complexity. So first, how do graph neural networks work? So if you have a graph here, I'll make it say 5 edges or 5 vertices like that. And we'll label these A, B, C, D, and E. Now, your graph is probably going to be sparse. In our case, it's fully connected because it's attention. But if we have a graph, I'm just going to have a graph where a few nodes are connected to A for now. So if you have a graph, you basically define, you have this or something like this. So you compose your graph of vertices and edges. That's it. Normal graph. So you have your vertices. In this case, V would be equal to, move that over a bit, A, B, C, D, C, D, and E. And then your edges, in this case, would be composed of A, B, AC, and AD. AD. Now, whenever you are dealing with a graph neural network, there are 2 phases. So the first phase is going to be message passing. Basically, for every node, it sends a message to every other node according to the edges. So let's say this is a directed graph. I guess in this case it would be BA, CA, and DA. This just makes it easy, but if it wasn't, then A would send messages to C as well. But in this first example, let's say it's just a directed graph that looks like this. So the first part is the message passing part. So our messages for A are going to be equal to, it'll be B, C, and D. So it'll be B, C, and D. Now, these nodes are not just nodes. Rather, we're going to have a vector for each one. You can think of this part as being the word the encoded word for the, and this vector being the encoded word for cat, and this vector being the encoded word for sat, and so on. So each of these actually has a vector. Now that is an ugly rectangle. E vector. And we'll denote these as, say, h sub a for the vector for a. So rather, the messages are going to be h sub b, h sub c, and h sub d. So these are our messages for a. Now our messages for b, let's say I'm going to define messages for b as well. Let's say E sends a message to b, and let's say D sends a message to b. So this would be h sub e and h sub b. So, and you do this for the rest of them. So m sub c, m d, and m e, and so on. Now each of these are, so each of these would have their own messages that they receive from other nodes. In this case, I only defined it for A and B, but you would also have it for C, D, and E. Now, usually one actually transform these features as they are sent across. So the messages would actually be, say, W, H, B, and W, H, W times W, H, B, and W times H, C, and W times H, D. And this would be W times H, E, and W times H, D, right? So basically, you're just transforming these in some way. Or it can just be a function, f of hb, and f of hc, and f of hd, to be more general in this sense. The function will be arbitrary, f of he, and f of hd. So another way to look at this is that you have your node A, and you have your three nodes here. So you would have B, C, and D, which each have a vector, C and D, which each have a vector, and then they send their messages to A. Oh, they send it to A through some function here, where this is actually the same function, so I'll just define it as one block, which is probably just a weight transformation or something like that. Now the second part here is going to be your update step. So update, and basically it takes these features here and it combines them. So you can define that as a sum or some other arbitrary function. An easy way is to just define it as a sum. That's usually what's done in the default graph neural networks, but that has issues. However, it's easy to define it as just a sum. So U of A is equal to the sum, psi is equal 1 to n of f of, we'll define it as ma of n, where the nth element is just that one. So it would be equal to f of hb plus f of hc plus f of hd. So basically, all that is happening is each node sends their vector. The vector is transformed. It is then summed up. So it's transformed and then summed up, where all these vectors are summed up after the transformation, and then that's sent to A, and you get your original, or then you get your updated vector for A. And this is all the message passing neural network does. So this is basically what's happening with attention, except the weight transformation here, the F, is a softmax over the messages sent. And the messages sent are actually sent over all the nodes. So you would also have E here, and then that would be sent through this function. And this function right here would be softmax over all the nodes. And then you do a weighted combination of those. So, or a linear combination of those. So that's all that's happening. Now, what they do is they say, okay, so we have this fully connected graph here. Now, what if we basically break it up into break it up into three parts, which will approximate this fully connected graph? So the way they break it up is actually quite simple. So they break it up into three parts. There's this first part here, which is just neighborhood attention. So you don't actually have this in normal attention. Basically, neighborhood attention says, like, if I were to define a graph already, then I send messages along that. So this is for a graph case, a graph problem with predefined relationships. In attention, you create a fully connected graph, you don't know the relationships. That's why you create a fully connected graph. But in this case, you have neighborhood attention if you have neighbors that are already defined. Now, the two things that they define to basically approximate this, the two other subgraphs they create, is this first one called the expander graph, and the second one called the global attention graph, or routing patterns rather, not graph. So this expander graph is actually a random graph that is constructed. Down here, they define it. So the random graph is quite simple to create. Basically, they pick d over 2 permutations of the vertices. So they just create a bunch of permutations of the vertices. D basically defines how large you want your graph to be. So if you have a larger D, you have more edges, but if you have a smaller, and it's basically better, messages are sent further, basically more routing of information. And if you have a smaller D, it's it's better computationally, but you don't get to send your messages as far, or as you don't have as many edges, so it may not be as good. So you create these permutations, so just permutations of the edges, or of the vertices, and yeah, of the n elements. And then all you do is you select some of those, or rather for each node. So for every node, you basically look at the permutation. So you look at every permutation. I have an example over here. You look at every permutation, and you select the ith node from the graph. So this is the ith node of the graph, and then you select the ith node in the permutation. And this basically just defines a set of random nodes, or a set of random edges. And the reason they do that is because they say that the resulting graph will be a d-regular near Ramanujan graph with high probability, or Ramanujan graph with high probability. Now, reading this off from Wikipedia, they basically say that this graph has a spectral gap that is as large as possible. So the idea for this is to send information far, according to what they say in this paper. So it creates this graph. It approximates this graph, which sends information far. So this is basically your local information passing, and this is your global, or not your global information passing, but a way to send information far into different nodes in the graph, which is necessary if you want to pass information from, say, the beginning of a sequence to the end of a sequence, or the middle of the sequence, which your local message passing would probably not do, unless you already defined it that way. But it likely wouldn't do that. And yeah, so then you have your global attention, and this basically defines one node, and this one node gets messages sent to it from everywhere, and it also sends information from everywhere, or to all the nodes. So this is kind of like a storage place. You can think of every node as kind of storing information in this node, and then it sending information from that node to the rest of the nodes. So like a storage area and a retrieval area for nodes. This is just for a global property. Yeah, and those are the three parts. They have the expander graph attention, which is what they call this, the expander graph, and they say it allows for propagating information between pairs of nodes that are distant in the input graph without connecting all pairs of nodes. And then they have global attention, so that's just one node, and they define very few of these. So if I have one node, that is order v, or order n, depending on how you want to define it. So if you have one node, it basically takes n messages. So if we have 1, 2, 3, 4, 5, 6, 7, 8, if we have 8 nodes, this one node here would take 8 messages, which is order n, or order v. And then if you have 2 nodes, it would be order 2v. or order, which is just order v. And if you have 3 nodes, it's still order v. Now, now you can't have too much of these because this is quite an expensive operation, so they only add a few of these. These, on the other hand, are a lot less expensive, and what they do is they combine all 3 of these to create this last graph here. And this graph is just a combination of the 3, which gives you the attention approximation they're going for, and they call this the Exphormer. This combination of the 3 mechanisms here: neighborhood attention, your local expander, a way to pass information far, and global, a way to have a place to store information and a place to retrieve information. And then local, just local locality. So that is it. They have so for the mathematical part, they have some very nice corollaries and lemmas that they define. And they have some nice properties of this Exphormer that they prove. So one such is this one: if a sparse attention mechanism has n nodes, is deregular and epsilon expander graph, then stacking O of log n transformer layers models all pairwise node interactions. It's not exactly O of log n. It's this here, but it's basically log n. So if you stack log n layers, then you get your full. Then you have basically a fully connected graph. It's going to be more than fully connected, but it's going to be at least fully connected. Oh, and I don't know why I forgot to mention this. This is linear in time. This right here is linear in time. This is linear in time, and this is linear in time. So in all, this is big O of v. So Exphormer is linear with the number of vertices you have, or the number of tokens you have in a sequence, which is a very nice property. Now, like I said down here, it takes O of log n layers. So at most, you would need n log n. It would be order n log n if you had log n layers to get a fully connected graph, which would be better than full attention because you likely have more connections. So that's likely more expressive than full attention with only O of log n, with only order O of n log n. So it's probably more expressive, and it doesn't require nearly as much complexity, assuming graph neural networks are not that computationally expensive, which they are in practice. They're more computationally expensive than a matrix multiplication, but in theory, it should be a lot. It should be a lot faster. In the worst case, where you have log n layers, it's actually better than that, and it's better than attention. So at least for the experiments they have. So they also want to see, they say a natural question is whether a sparse transformer model based on the Exphormer allows for universal approximation of functions, and that's because dense transformer models are known to be universal approximators. So even if you can get this fully connected graph, is it a universal approximator? And they do show in the appendix that universal approximation properties for dense transformers do not hold for sparse transformers, but they show every continuous function can be approximated to desired accuracy by Exphormer networks using either global attention or expander attention. So this is just a function, rather, it can approximate any function of this type. So every continuous function, which is it's pretty good. That's probably a fair assumption. And yeah, those are the 2 things that they show. So 2 very good properties that they prove in the appendix, if you're curious. And yeah, let's check out how well it does. So this here is normal message passing. MPNN is message passing neural network. Big Bird, if you've heard of Longformer, it's similar to that. And then Performer And then they have transformers. So this is full attention. These two are sparse. Big Bird and Performer are sparse. And this is on these are just on 4 data sets they picked. And it does pretty well on all of them. So green is first place. I think orange is second, and blue is third. So it gets first place on this data set by a significant margin over the full transformer. It gets second place on this one it gets first place on this one over the full transformer, first place on this one, and second place on this one. So it does really well, and the second place is very close to the first place one. Now they also test, does this work well on long range data or long range graphs, where you have to send information you have to send information far, and they show that it does do that, because that is a very big desire for a transformer. It should send information far. And they show it gets first place, second place, first, and first. So it's very promising on these benchmarks that they have. And then for large graphs, it doesn't run out of memory. So a lot of so these are full attention graphs, and these are just some message passing neural network, and it does not run out of memory for those, while the full attention does. So that's a property that they show is very, very nice about this. It doesn't use anywhere near as much compute as full transformers do, but it is just as expressive. Yeah, and then they also show the last thing they show. They show a few more nice properties about this, such as down here. Here we go. So it's also a lot smaller in size. So for instance, on this data set, the Exphormer model was just 90,000 parameters compared to 340,000 parameters in the full transformer model. So it's a lot smaller, it's a lot faster, and it sometimes outperforms other models, which use full attention. So it's looking very good for this model, and I'm very curious how this will actually do on a real data set, such as using it in a model like Llama. I'm curious how this might perform, or on a really large, like actual data set, because from these benchmarks it looks really good, and it's a lot faster. If you're curious, they have a lot more data on here, such as how how large the models are, and like the time it takes for each of these models to run. And then the proofs are down back here as well. But yeah, that's it. It's pretty basic. You're just creating these 4 sparse routing mechanisms, combining them all, and you have your attention mechanism that is linear, and it approximates full attention, or it approximates a fully connected graph with log n layers, or with log v layers. So it's a very cool paper to see that, or it's very cool to see this approximate method work so well. Other methods have not. So I'm very excited to see if this one actually works well as they say it does. Yeah, so we will find out. That's Exphormer.